Good morning, good afternoon, actually. I'm Guillaume. I'm going to present my PhD, which is on the subject of aeroelastic tailoring, especially using structural member shape and structural arrangement. This work is supervised by Jonathan Cooper and Paul Weaver. So what is aeroelastic tailoring? Well, aeroelastic tailoring is quite simply the positive control over aeroelastic performances. And aeroelastic performances are things like the deformation of the wing during maneuver, during a gust encounter. And we're interested in that because that generates stresses, and those stresses often end up being the load case for which we're going to size our structure. So if we can reduce the stresses, we can therefore reduce the weight on the aircraft. Aeroelastic performances are also interested in things like the first aeroelastic instability speed that some of you might know as being the flutter speed or the divergence speed. And that's things that occur at the edge of the flight envelope. And that also has an impact on the weight of the aircraft. So in my PhD, I looked into three novel ways to control aeroelastic performances. The first one is to use curvilinear structural members. So that means curved spars, curved stringers, and curved ribs. The second one is to use the structural arrangement. So here it's really the angle that different structural members are making with respect to one another. So it can be the angle between the ribs and the spars, it can be the angle between the spars and the stringers, and so on. Now the last one, which is a bit more exotic, is crenellated skin. So crenellated skin is a skin of varying thicknesses in the spanwise direction. And we're interested to see if this concept can impact our elastic performances. Now we also compared this novel concept to a benchmark concept, which is the use of the composite stacking sequence. And the reason we use that as the benchmark concept is because actually aeroelastic tailoring originated from the use of composite stacking sequence to control aeroelastic performance. So the ongoing work has two different streams. The first one is on simple structure. So here the structure is untapered and unswept. And here we try to characterize the bend twist coupling capability of the different concepts. To do so, we use high fidelity modeling, such as finite element. And the results that we get from the modeling, we are trying to validate them through an experiment that uses 3D printed wings and digital image correlation. Now the second stream looks at applying this concept to complex structure. So complex structures are things that are swept back or swept forward and that also have a taper ratio. And here we're trying to understand the advantages that this concept could bring to a real-life design. To do so, we once again use high fidelity modeling, and we also use optimization methods to actually converge quickly towards and identify a better design. Those are just examples of some of the results that we found in the past 2 years. We show that you can actually increase your flutter divergence speed. The amount by which you can increase that speed depends on how much freedom you have in your design space. We also proved that you can decrease your root bending moment during a gust encounter. And also, we found that you can actually increase your minimum buckling eigenvalues during a 2.5G load case. So, in conclusion, well, we proved that actually those concepts do offer you a way to control the bend twist coupling of the wing. And that was related to increasing some aeroelastic performances, such as the flutter and divergence speed, and decreasing the root bending moment during a gust encounter. The future work in my PhD is really to try to close the gap between the tools that we used in my PhD and the decision variable set that we use. Because you see the tools that we used are normally developed around what's known as the detailed design phase in a common wing design project. However, the decision variables are set much earlier, somewhere between conceptual design phase and preliminary design phase. Hence, we need to come up with a tool that will actually enable engineers to actually try those concepts at those sort of stages in the design process, and therefore see whether those concepts have any advantages for their future wing concept. If you're interested to learn more about my research, please come and see me about my poster. With that, I'd like to thank you for listening. I'd like to thank my supervisors, the EPSRC, and also the EOARD for their support. Thank you.